Hey all, it's Ms. Blasky. Today we are going to talk about some thermodynamically important measurements that are not heat. So one of the things that we can measure or talk about a chemical reaction is whether it is spontaneous or not. And so spontaneous, this is sort of the old-fashioned term. The new term is thermodynamically favorable. When we talk about whether a reaction is spontaneous or thermodynamically favorable, we are talking about whether the reaction will occur on its own. We're usually talking about the forward reaction, the way it's written on the paper, if that will happen without any additional energy requirements on that system. So as soon as I mix those chemicals together, is the reaction going to happen? So things that we know of that are spontaneous reactions are the fact that hot objects will spontaneously cool off. So the process of transferring energy from a higher energy substance to a lower energy substance is thermodynamically favorable. It likes to do that. We don't normally use the word like or dislike, but it is favorable. It is the way that it will happen on its own. When we take baking soda and vinegar and we react them together, the reaction occurs. That reaction is thermodynamically favorable to form its products. Right. So we're going to try be in the habit of saying thermodynamically favorable when we're talking about this. Every once in a while, I might slip and say the word spontaneous, but I will try and fix myself when I say that. So to figure out whether a reaction is thermodynamically favorable or not, there are two other variables we need to consider in addition to the enthalpy, the heat that we were talking about previously. So first, we need to talk about a measurement called entropy. So entropy is handled with what's called the third law of thermodynamics. Entropy is a measure of randomness or disorder of a system. So when a system becomes more disordered, we say its entropy increases. So we can talk about this in several different ways. In chemistry, we're talking about the order or disorder of the particles, the atoms or molecules inside that system. So if I take liquid water and turn it into a gas, that is increasing the entropy. Those gas particles are more random, they're more spread out, they're more disordered. So the entropy of that system has increased. If I take a solid and dissolve it in a liquid, if I take salt and dissolve it in water, I am increasing the entropy because those molecules had all been all nice and orderly and structured in that solid. And now those ions, so not only have I broken apart that molecule into more pieces, but now those pieces are also now randomly scattered throughout that solution. So that would be increasing the entropy. If I make something more ordered or I take away some of the randomness, then my entropy is negative. So if I freeze that water, if I take liquid water and I freeze it into a solid, that entropy would be negative. I'm making that system more ordered. So there are some fairly common changes in entropy that you need to be able to recognize. So phase changes, solid melting or liquids evaporating is going to increase the entropy. Dissolving solids in solution, we talked about this one, that is going to increase your entropy. When we have something that stays the same phase but makes more particles as a product. So for example, a gaseous chemical reaction produces more molecules on the product side than it had on the reactant side because there are now more particles. That is going to increase the entropy. Increasing the temperature of a substance increases the entropy because we have more molecular motion in those particles. And so that is increasing the disorder. And in general, entropy increases as we make molecules more complex. So if we have more ions in an ionic substance, if we have more atoms in a molecule, because there are that many more bonds, that many more atoms, that many more protons, neutrons, and electrons, that is increasing the entropy. Right? Entropy can be calculated just like we calculated our enthalpy. You got to be careful with those two words because they're really close to each other, by finding the sum of the entropies of the products minus the sum of the entropies of the reactants. So just like before, there's going to be a little data table telling you the pieces that you need, and we would multiply them by the coefficients, by the number of moles we have, just like before. Now notice that entropy has a little bit different unit on it. Entropy is measured in joules, not in kilojoules. And it's not just per mole, it's per mole Kelvin. Because entropy is dependent on temperature, we need to keep that temperature dependency in there. So just be careful of that when you are writing out your units. So to calculate the entropy change for this particular reaction, delta S is going to be 2 times the entropy of liquid water minus 2 times the entropy of hydrogen and the entropy of oxygen. Again, these are given to us in our data table here. Even standard state substances do have entropies. The only time we do not have an entropy, and I think it's up here, let's circle it. The entropy of a pure solid at absolute zero is 0. So the only time that we can have a 0 entropy is when we have no molecular motion whatsoever. Any other substance is going to at least have molecular motion, and so that still is going to have some amount of entropy to it. So 2 waters, 69.9, minus 2 hydrogens, 130.6, minus an oxygen, which is 205. And we can calculate our overall delta S. So again, be very careful with your signs. So I've got 139.8 minus, I don't need a parenthesis there. $466.2 gives me an overall delta S value of negative 326.4 joules per Kelvin. No moles in there because we already took care of the moles by multiplying by their coefficients. Now notice that this delta S is negative. Negative delta S means more ordered or less disordered, which makes sense. I took 2 gaseous elements, technically 3 gaseous particles, combine them together into a liquid. So this is becoming more ordered. The second measurement that is needed to help us determine whether something is thermodynamically favorable or not is this measurement called Gibbs free energy. Gibbs free energy doesn't really have a definition that we need to care about like enthalpy and entropy do. Gibbs free energy is just a number to us, and that's all we really care about. So the change in free energy helps us know whether the reaction is thermodynamically favorable or not. So if delta G is negative, that reaction is thermodynamically favorable. If delta G is positive, the reaction, the way it is written, is not thermodynamically favorable. But if we reversed the reaction, the reverse reaction would be thermodynamically favorable. If we get a problem or a chemical reaction that comes out to be exactly a delta G of 0, that means that that reaction is perfectly at equilibrium, which means we do not have a spontaneous change in either the forward or the reverse direction. We can calculate delta G the exact same way that we calculate delta S and delta H. Delta G of the products minus delta G of the reactants. I'm not even going to go through that because I think you can probably figure that part out. The part where it does get interesting is if we look at page 17. Entropy, enthalpy, and Gibbs free energy are all connected to each other. So whether a reaction is thermodynamically favorable or not, that delta G, is dependent on the enthalpy of the reaction. Is it endothermic or exothermic? The entropy of the reaction. Is it increasing or decreasing its order? And the temperature at which that reaction is taking place. So based on this mathematical relationship, we have a whole bunch of different combinations of the mathematical signs of delta H and delta S and how that's going to affect my delta G. So if I have an exothermic reaction and that reaction is becoming more disordered, meaning that delta H is negative and delta S is positive, that is the ultimate definition of an always thermodynamically favorable reaction. There are some people who talk about, especially when we talk about that third law of thermodynamics, that say the universe tends towards disorder. The universe is always wanting to sort of calm itself down, spread itself out. Lots of times, this isn't a perfect example, but we talk about how if you drop a glass, it is much more likely for those glass shards to scatter all over the place than it is for them to form a nice tidy pile. Right? So the universe tends towards disorder. Exothermic means it's releasing its energy, and then a more disordered reaction that is much more thermodynamically favorable to the system. If the opposite is true, if we have an endothermic reaction that is becoming more ordered, that is sort of the opposite. That's the antithesis of a thermodynamically favorable system. Now, if we have different signs on our delta H and our delta S, this is where temperature dependency comes in. So that it can be thermodynamically favorable at a high temperature or versus a low temperature, depending on the combination of your delta H and your delta S. Now, this is all mathematical. We can prove this all from that equation. But just to sort of summarize everything, use these two tables. So down at the bottom, a reminder of what delta H's signs and delta S's signs mean, just in case you need it. So if I have an exothermic reaction that is more disordered, that is always going to be thermodynamically favorable. If I have an endothermic reaction that is becoming more ordered, that is always not going to be thermodynamically favorable or thermodynamically unfavorable. When my signs match, this is where temperature dependence comes in. So if I have an exothermic reaction that is becoming more ordered, it will be thermodynamically favorable at low temperatures, but thermodynamically unfavorable at higher temperatures. And then if I have an endothermic reaction that is increasing its disorder, it will be not thermodynamically favorable at low temperatures, but favorable at high temperatures. This combination of math shows up all the time on multiple choice questions. And we will practice this a whole bunch on multiple choice questions. So we can do some calculations or look at some reactions to coordinate all the values of delta H, delta S, and delta G. So for example, let's take a look at number 57. says predict the effect of increasing temperature on the spontaneity of the reaction below. If I increase my temperature, we need to think a little bit about equilibrium here. We need to think a little bit about particle motion here, in addition to the things that we've been learning about entropy and enthalpy. So this particular reaction, I start with 2 gaseous reactant molecules, and then I have 5 gaseous particles as my products. So if I increase my temperature, I am going to make this substance much more disordered. So if I am making my delta S much larger, then I'm going to all of those particles are going to be moving around much more. So my spontaneity is going to increase. The more disordered I am, the more thermodynamically favorable I am going to become. As opposed to number 58, I have all gas particles. My products have fewer gas particles in it than my reactants, which means I am becoming a more ordered system. Now, pulling in some math with this, here I've got some information about delta H, some information about delta S, and they're asking me to calculate each one of those and calculate delta G. So this is putting together all of the math that we have done pretty much so far this whole chapter. So to find my delta H, I need to take products minus reactants. So I've got 2 of my SO3s, which is negative 396 kilojoules, minus 2 SO2s minus my reactants, which is negative 297, and an oxygen, but oxygen is 0, so I can leave that out. So I've got 2 times negative 396 gives me negative 792. And then I've got 2 times negative 297. So minus negative 594. So I have to add the 594. Gives me a delta H value of negative 198 kilojoules. Do the same for my entropy, my delta S, products minus reactants. So 2 times 257 minus 2 times 248, and then a 205. Now remember that these have joules as their unit instead of kilojoules. So 514 minus 701 gives me a delta S value of negative 187 joules per Kelvin. Oop, and that was standard. So now to find my delta G, if they gave me delta G values for each of my reactants and products, I could just calculate it the same way I did here. But I can also do delta G equals delta H minus T delta S. So delta G is what I'm trying to find. My delta H was 198 kilojoules. Now notice that is kilojoules. I need to make my kilojoules and my joules match up. It doesn't matter which way you go. I tend to leave things in kilojoules and change that delta S into kilojoules. So my temperature needs to be in Kelvin because my unit on delta S has Kelvin. So 25 plus 273 gives me 298 Kelvin. And then if I convert 187 into kilojoules, that's negative 0.187 joules per Kelvin. So now I do my calculations. So 298 times 0.187 gives me negative 55. Negative 198 minus negative 55.726. So I have to add those together, and I get that my delta G is negative 142 kilojoules. So from all of these numbers, I can identify that because my delta H is negative, this is an exothermic reaction. Because my delta S is negative, it is becoming more ordered or less disordered. And because my delta G is negative, I know that this reaction is thermodynamically favorable. So there's a lot of coordination of numbers there. Now, I'm sure you could see this coming, but in the last section, we can connect delta G to equilibrium. If we're talking about whether things are thermodynamically favorable or not, we should be able to connect this to whether our forward reaction is happening or not. So we've got this equation that connects delta G to equilibrium. So what this means is that if K is big enough, when I do this math, the natural log of a large number multiplied by R times T, T is temperature, R is constant, that value is going to become negative. We'll see that delta G stays negative and that reaction is spontaneous. If K is a small number, when we take the natural log of that, we get a negative answer. So negative times negative is going to cancel each other out. A small k is going to give us a positive delta G, meaning that that reaction is not thermodynamically favorable. So we can compare these. Again, this relationship is very important back and forth. Either if I know my K, I can go ahead and figure out my delta G, or vice versa. If I know my delta G, I can find K. Now, the R value in here, on your equation sheet, you have an R value that has joules in it, which is the R that we're going to have to use. This is not the 0.00821 that we normally use for gases, even though that has the same variable. We're running out of alphabetical letters. We got to start doubling up somewhere. But so we're going to use the R value that has joules in it because we are talking about energy, right? So that's a lot going on, but these questions all get wrapped up a lot together. I wanted to put it all into one video because they all are related to each other. We're going to spend a long time working our way through all this and seeing how all this applies to AP style questions. As always, if you need any help, let me know, and I will talk to you all later.